Okay, happy Thursday, Ty and Ben. Um, Yesterday's recording failed, and so I'm going to have to redo those problems. And actually, since on a couple of them I got a certain distance and found out they wouldn't work, I'll just write new problems that have solutions right from the get-go. And it'll be a shorter recording, but I'll have to redo those maybe this afternoon, otherwise tomorrow. And that'll work out. I wanted to start today by looking at a couple of YouTube videos, or probably just one YouTube video. And it has to do, there's a little bit of discussion in the chapter on rotational motion on generating artificial gravity. And most science fiction TV shows and movies that you watch, they don't even mention it, or they say, we just have artificial gravity. And they never say how they generate it. But every once in a while, you'll see a movie or a TV show that generates it in a realistic way. And they may not get the numbers quite right, but at least they'll get the concept right. And the first movie that I know of that had it was the movie 2001, A Space Odyssey, which actually came out in I think it was 68, if I remember right. Could have been late 1967, but I can remember my 8th grade science teacher talking about the movie. And it was probably in the last half of the year, as far as I know. But anyway, that's the first one I knew of. And then, let's see, recently the movie The Martian had realistic artificial gravity. At least the concept was there. And yeah, there haven't been many others. I've been watching a TV series for the last few years that comes out seasonally. It's on Amazon now. It started off on the Sci-Fi Channel, but it's called The Expanse. And the way that they generate artificial gravity in their spaceships is to continually accelerate. And that would do it. And we could look at an example problem like that. And then they accelerate continually halfway to wherever it is they're going, and then they flip the ship around and decelerate continually to generate artificial gravity on the way in. And so they have that, or they generate it on asteroids by doing what they call spinning up the asteroid. And spinning up something is what's looked at in this little video that we have here. So I'll show you what that looks like. Let's see, share the screen 2. And I may just blow up this YouTube video to have it full screen here, except where's the play command? It's hiding down under this. I must have some urgent message. Yes, maybe. Nah, that's not urgent. Okay. Anyway, we'll play this thing.
Basically, the Martian, the Hermes, uses ion engines. We've never actually used those in humans.
Oh, can you hear the narrator, by the way? Did you know he was talking? Anybody?
I didn't hear anything.
Okay, maybe I'll see if I can turn it up or change the audio on my Zoom recording to same as system for the time being, maybe. And then when I start playing this thing, tell me if you hear anything.
But NASA's unmanned mission Dawn used them to visit asteroid series. Really efficient.
Hear anything?
Yeah, I can hear it.
Okay, so now you got narration. All right, I'll back this up a little bit here. And about there.
That's what's Mars. Yeah, Mars.
Mars travel is no joke. It's so far away, it takes radio signals traveling at the speed of light between 4 and 24 minutes to get there from Earth. So communication is more like a text message with a busy friend than a phone call.
Incoming.
Most movies gloss over this, but it's a major plot point in The Martian.
Are you receiving me?
32-minute round trip communications time. This won't exactly be an Algonquin roundtable with snappy reporting.
Space travel is much slower. The spaceship in The Martian, the Hermes, uses ion engines. We've never actually used those in human spaceflight, but NASA's unmanned mission, Dawn, used them to visit the asteroid Ceres. They're really efficient, letting you minimize fuel and allow you to constantly accelerate. So that's exactly what you need for a Mars voyage. Even still, it might take something like 500 days for a round trip.
Seriously though, Rick, how do we get there?
Well, you basically point the bird in that direction. You wait 150 days, and 36 million miles later, we should be at Mars.
That lonely weightlessness wreaks havoc on your body, so you want them to have artificial gravity. Here in the demo space of the University of California, Santa Barbara. On the way to Mars, the astronauts live in this giant wheel that's giving them artificial gravity. How does it work? Well, we can use this trick that every kid knows. Put water in a bucket, and if we turn this bucket over, it would fall out because of gravity. But if we spin it around, we can generate acceleration that can counteract gravity. Let's see if it works. All right, look at that. The acceleration of me swinging it around is actually keeping the water in place and counteracting gravity. If I spin it faster, I get more gravity. If my arms are longer, I get more gravity. So the Martian is realistic. To create artificial gravity, you spin a giant wheel. Did they get it exactly right? When Andy Weir saw the trailer, he did some calculations.
So when the trailer first came out, I did a bunch of freeze frames measuring against Cape Mara's height so that I could calculate the radius.
I estimate the radius of the wheel is about 8 Cape Maras, or 42 feet.
And the rotation, I figured out they would actually only have about 0.2 Gs. But it doesn't matter. The point is, if they have gravity, which is the main problem. Yeah.
Now let's talk about sticking the landing.
Okay,
Rob Manning.
now I have to switch my microphone back, I think. Okay, now they're talking about other stuff. This whole thing is about addressing the physics of the movie The Martian, and so we won't worry about the rest of those things. But now I'm going to minimize this and get back to something else. And I can't move it, minimize it till I get it out of the way. There we go. Okay. I wanted to talk a little bit about artificial gravity, and I'll post this file up here in a little bit if you want to watch those. There's another link up here. I can't remember what it's called. It's a PBS series on science, and the guy on there talks really fast, but you may recognize some formulas that we're going to use. Maybe before we get to that, I want to talk about just what it takes to make something move in a circle. And let's suppose something is undergoing uniform circular motion, so it's traveling in a circle like that. Well, if this is a radius r, it's going to have centripetal acceleration given by v squared over r, or capital R. If it's traveling in that circle, that's its acceleration. In order to have that acceleration, the acceleration is going to equal the applied force on it divided by its mass. And so you will need a force, F equals ma, which in this case is mv squared over capital R. It will take a force to make something travel in a circle. Now, sometimes that force is going to be, if you've got a giant metal disc that's spinning, that force will be provided by the electromagnetic attraction between the atoms in the disc, and that's what will hold it together. If you have something else going on, it's going to have to be provided by something else. In the movie 2001, A Space Odyssey, there was a space station that was shaped like a giant wheel. Man, I could probably, oh, it'd get busted if I tried to post it to YouTube for you guys. But there's a space station shaped like a giant wheel that's in space, and it's rotating, and the passengers are actually standing on this part of it. And it's something similar to the science fiction series on Amazon that I was telling you about, The Expanse, where they build a structure on the outside of an asteroid. This would represent the asteroid. And then they build something there and spin up the asteroid. And this is where people stand. Okay. And what provides the force that generates the acceleration that they experience is the contact force between their feet and this outside wall. If that wall wasn't there and they were moving at that speed v, they would move in a straight line with constant speed. Okay? It takes a force to make them travel in a curved thing, and that force is provided by the normal force. So if you look at them there, the forces that are acting on them, actually, there's one. It's the normal force. And they've got acceleration toward the center of the circle of the thing because they're traveling in a circle. And so that normal force, which is equal to ma, is going to equal in magnitude, the normal force is mv squared over r, whatever their radius is. I used a capital R, so we'll use that. So the higher their speed, the greater that normal force is going to be. And what they want it to, the normal force to equal is the same acceleration that they would be experiencing on Earth, possibly. Sometimes they settle for smaller values of g, and or smaller values than g, so they experience maybe 3/10 of a g or 4/10 of a g, something like that. And I think they just mentioned in that video clip we saw that the dimensions of the one in the movie The Martian was enough to give it about 2/10 of a g of acceleration. So that's not bad. I've actually had my physics students, engineering physics students, when we study this fall quarter, is watch parts of the film, and I'll put it on a loop so it just repeats and repeats, and try to figure out just how much of acceleration they would be experiencing with the rotation of that spaceship in there. And that movie did a pretty good job, I thought, as far as the physics. You know, the numbers may not have been right, but the concepts were believable. And so they got something off by a factor of, you know, a few. The ideas were okay. So there's that thing. Anyway, you can do this with a rotating spaceship or spinning a bucket around. I can remember as a kid filling a bucket with water and swinging it around like that. And we would actually, one of our neighbors had a little berry bush that they weren't edible berries, but we'd pick the berries off of there and put them inside the bucket and spin the bucket around and then let go. And it was the crashing spaceship. And we'd see how many survivors there were. This is really black humor, but it was the survivors were the berries that didn't get smashed on impact. And so then we'd take all the smashed ones out and do it again, see how many survived the next crash. And kids, I don't know how it works, but that's experimenting with physics. And you can generate artificial gravity by having a spinning structure. Let me do a real quick search and see if I can find that scene from the Space Odyssey. 2001 space station interior scene. Here it is. This is a very 60s movie. And you can kind of tell by, oh, suits and things like that. Oh, the sound doesn't matter, actually. We can kind of narrate over this. But something to notice is that the floor is curved. You're on the inside of this curved structure, and the center of it is over your head. Let's see, I don't know. Maybe, yeah, you can see how the floor is curved in this scene, looking far away toward those other chairs. Yeah, this one doesn't really show very well. Let's see. Oh, here's the space station scene, or a space station scene in there. Centripetal force to simulate gravity. Yeah, so they're on a spinning wheel so they can keep some semblance of that. Okay, and this is the, it's PBS Space-Time is the one that talks about the most realistic artificial gravity in sci-fi. This guy talks really fast though, so fair warning. All right, now, because we've got a V in here, we can actually solve for this thing a little bit and do some stuff with it. Now, the speed that you're going at when you go around here, we're gonna let the circumference equal 2 pi r. That's the formula the Greeks figured out. And the period of rotation is equal to, I'm just going to use a capital T for it. And so what we will get out of this is that that acceleration they're experiencing, the v squared over r, capital R, is going to equal, v is going to be 2 pi r divided by t. So we'll have 2 pi capital R divided by t, and remember v gets squared, and then we're multiplying that by 1 over r, and so we'll end up with square everything inside, 4 pi capital R, pi squared over t squared. Let's see, it would be r squared here, but we divide by an r, so we lose one, something like that. Now, the angular velocity happens to be omega is equal to 2 pi radians divided by the period, okay? In one period, the thing will rotate through 2 pi radians, and so we already saw this the other day. This 4 pi squared over t squared ends up being equaling omega squared capital R. So we can either write that acceleration formula as v squared over r, or we can write it as omega squared r and do things like that. Let's see, the period t happens to be the reciprocal of something called the frequency. T, capital T, happens to be the time per revolution. The reciprocal of that is the number of revolutions per unit time. And so if something is completing 50 revolutions per minute, then the reciprocal of that would be 1/50th, and the period ends up being 1/50th of a minute. So we won't worry about that too much, but let's dive into some problems here. Suppose a wheel-shaped space station has the passenger's feet 100 meters from the rotational axis. How fast must the passengers be moving in order for them to feel 1 g of acceleration? Well, this means that the acceleration they experience is equal to g, but the acceleration they experience is v squared over r. And we're given that r is 100 meters. And so what we don't know is v, how fast they happen to be moving. Well, we can figure that out. V squared is going to equal rg, which is going to be 100 meters times 9.8. We'll just use 9.8 for this, meters per second squared. In fact, we'll probably round to one significant figure when we're done. Well, 100 times 10 is about 1,000. It's 980. And if I take the square root of that, this would be 980 meters squared per second squared when I multiply these two things together. Or the speed they'd have to be moving at is square root of that. Whoops, I did not push the right button. My calculator tells me it's 14 times the square root of 5, or 31 meters per second is about how fast they'd be going. Now, when that condition is met, how long will it take the space station to complete one rotation? Well, that speed, v, is equal to 2 times pi times the radius of it divided by the period. Okay, this is the circumference. They travel that circumference in one period, and v is distance traveled divided by time. So I have that. Or the time, if I multiply both sides by t, I get vt equals 2 pi r. Or that time for one rotation is going to be 2 pi r divided by the speed. So 2 times pi times 100 meters divided by that 31.3 meters per second. And I can punch that into my calculator. We can see what we get. 2 pi times 100 divided by the answer that I just calculated. And I get about 20 seconds. Okay, that could be a problem. That means you'd be traveling all the way around this circle in 20 seconds. You probably shouldn't have windows that people can look out of when they're spinning that fast, because people get motion sickness pretty easily when they're rotating. And what can trigger the motion sickness is seeing the motion relative to something else. Sometimes you don't even have to be moving. I think I mentioned the other day that I get motion sickness from spinning. I get motion sickness by looking at, I don't even have to be spinning. When we visited Japan, oh man, it's been about 15 years now, but we were riding on the bullet train. And if I looked out the side window of the bullet train at close-up scenery while you're going at 180 miles an hour, just seeing that stuff go by me sideways was enough to make me dizzy, and I had to look away. I couldn't do it. If I looked at something that was quite distant, it was okay. Like if I looked at something a mile or two away, no problem with that. But it was just the stuff that was only 10 or 20 or 30 feet in front of the window that bothered me. So that could be a problem here. I even got sick. Used to be in the library, they had microfilm readers, and microfilm would be this long strip of plastic film that you loaded into a machine, and then you would turn a crank on the machine, in the old ones, after a while, I think you could push a button, but it would take these pages, go flipping past your eyes. And if I used that thing for very long at all, I had to take a break because just that motion of the stuff going by my eyes was enough to upset my equilibrium. So did not like it. Okay, let's try another one here. We have a 22-kilogram child riding a merry-go-round, playground merry-go-round that's rotating at 40 revolutions per minute. So that's omega. It just isn't in convenient units for it. What centripetal force must she exert to stay on if she's 1.25 meters from the center? Okay, well, if we have this child sitting on the merry-go-round and anyway, she's sitting there like that, and here's the center of the merry-go-round, and it says she's 1.25 meters from the center of it, right? Her centripetal acceleration is going to be in this direction. Now, the forces that are acting on her will have mg downward and a normal force upward. So those two forces, and they actually cancel out. There's got to be another force, and that force is the frictional force that's provided by the contact between her and the merry-go-round. If there was no frictional force, she would be flung off the merry-go-round at whatever speed it's spinning where she happens to be. She would continue with that speed in a straight line and constant direction, and she gets flung off the merry-go-round. That's Newton's first law. Now, we will invent at times a fictitious force to say centrifugal force, or centrifugal force flung her off. But it wasn't centrifugal force. It was Newton's first law. Objects in motion will remain in motion with constant speed and direction. And looking down from above on this child who's sitting there, there's the child now. She's drawn as a block. If this thing is going with some velocity at some time and there's no sideways force on it, it will be flung off of the thing. You can also spin the object fast enough. That means giving it a bigger V so that the frictional force goes beyond being maxed out, and instead of having static friction, you have kinetic friction acting, which is weaker than static friction, and she'll be flung off again. So we don't want that to happen. But anyway, 40 revolutions per minute. Okay, here it's a bigger one. But 40 revolutions per minute is omega. So we need to convert that into radians per second to be able to work with it. So 2 pi radians per revolution times 1 minute over 60 seconds. And then we'll have radians per second. The minutes divide out, the revolutions divide out, and we'll be good to go. 40 times 2 pi divided by 60 is we've got 3 significant figures, so 4.19 radians per second. And the centripetal force she needs is going to equal, has to be her mass times the acceleration she's experiencing. Her mass, well, the acceleration in this case is v squared over r or omega squared r. So we've got it handled with that version of the formula. Then we just plug in the numbers. Mass was 22.0 kilograms. Omega was 4.19 radians per second. and we square that, and the R was 1.25 meters. And actually, when you square this 4.19, you're going to get something about, well, more than 16 anyway. Multiply that by 1 1/4, and you're going to be up past 20 meters per second squared. In fact, we can calculate it. Oh, I had 4.19 in there. Oh, well. Square it times 1.25. And yeah, 21 point, actually about 22.0 meters per second squared. That's 2 Gs. It's hard to be on one of these merry-go-rounds when it's spinning that fast, especially if it's going to keep spinning. If you try to pull yourself to the outside of it, it's hard. It's hard to pull yourself out there when you're experiencing an acceleration like that, because your weight effectively doubles, or the force you're having to work against to move your weight there is twice your normal weight or more in this case. So we forgot to multiply by 22, and we get 483 newtons. So, and compare that to her weight, which is mg. It's just going to be 22 times 9.81. So it's about 216 newtons. Okay, so this force has to be more than twice that. Now, you can't do this with just friction. There'd have to be some kind of bars on this thing that let the kids hang on. Otherwise, all of them are going to get flung off it when the big bullies come and spin the thing up really fast. So, got to watch out for that. All right, so what centripetal force does she need to stay on an amusement park merry-go-round that rotates at 3 revolutions per minute if she's 8 meters from the surface? Something to notice here is that this force increases with increasing radius, and so does the acceleration. It's omega squared r. So if you're 8 meters and it was spinning at the same speed, as opposed to 1.25, you'd have whatever 8 divided by 1.25 is. It's about 3 times as much or more than 4 times as much. Let's see. Yeah, 6.4 is how much it happens to be. And that's quite a bit. So, but this one's down here is spinning slower. It's only 3 revolutions per minute. So 3.00 revolutions per minute. And I write these unit conversions out every time, so you get in the habit of seeing them and try to get in the habit of doing them as well. Times 2 pi radians per revolution times 1 minute over 60 seconds. Revolutions go away, minutes go away, and I'll get radians per second. So 3 times 2 pi is 6 pi divided by 60. So and imagine that. It's 0.314 radians per second. That's omega for her in this case. And then the centripetal force that she experiences is going to equal ma again, but the acceleration is omega squared r again. So m omega squared r, so those 22.0 kilograms times this slower radial speed, 314 radians per second, and that gets squared, that's the omega squared, and then 8.00 meters. Whoops, 22 times the answer squared times 8. Okay, this time I only get 174 newtons, and it would be kilogram meter per second squared. Remember, the radians are just a placeholder unit. So 174 newtons, which is less than her weight. Okay, things that are in amusement parks, they kind of have to back off on the forces. This one that's in the playground merry-go-round, that's muscle powered. So the children usually spin it up themselves, and so they don't tend to be going fast enough to actually be dangerous. Although there's lots of things that happen at just playgrounds. Kids get bonked and stuff like that. So any questions on that problem?
How did you get 174 newtons? Because I keep getting 17.4.
Hey, you are right. I read my calculator wrong, that's how. It says 1.737 E1, and I was, for some reason, thought it said E2. So yeah, 17.4 newtons, which is, that's much less than her weight. And so that's not going to be a very extreme one. So it's safe to have little kids on the ponies on the merry-go-round, and they're not going to be in risk of anything except just falling straight down onto the thing. Okay, well, this ought to be fun. We have a ladybug on a flat turntable that is gradually speeding up, and there is a coefficient of static friction between the ladybug and the turntable of 0.87. Will the ladybug be more likely to slide close to the center of the turntable or out near the edge? Well, let's make ourselves a free body diagram, and I guess it can be when the bug's over on this side of the thing, and we'll look at it from the side. So we'll put ourselves in the plane of the turntable and look at it there, and make a free body diagram for the ladybug. We have mg downward. Okay, we'll have the normal force up, and if the ladybug is going to slide, it'll slide to the outside, and the friction will oppose that sliding. It's going to have to be in toward the center of the merry-go-round here, or turntable, and so this will have to be the direction of the frictional force. Now, they don't give us the mass of the ladybug, but it's going to disappear for us, and I'll show you why. If I say that X is toward the center of the turntable and Y is perpendicular to the surface of it, and again, I'm using this viewpoint from the plane of the turntable here, the sum of the forces in the Y direction, with positive being upwards, would just be N minus mg, and nothing happens in the Y direction. It's all going to be in the sideways direction. So those will equal 0, or the normal force is going to equal mg. Now, the frictional force is going to equal, in this case, we would want to be static friction. Okay, and we're interested in maxing it out, having the maximum amount of friction. And so that will be mu sub s times the normal force. And it's that frictional force that will provide the centripetal acceleration. So that'll be the mass of the ladybug times its acceleration. Oh, by the way, generally the frictional force is less than or equal to this, but we want to have the maximum amount of friction, and so we'll use the equality here. Usually it's got a less than or equal to on it. Whoops, that looks like a person's face. Huh, that's probably the best cartoon I ever made. Anyway, it was supposed to be a less than or equal symbol. Now, the normal force is mg, so we'll have that mu sub s mg is equal to ma. And this is the centripetal acceleration, but the mass divides out, and it turns out the maximum acceleration you can have using friction ends up being mu sub s times g. That's worth noting here. That's the biggest acceleration you can have. And that centripetal acceleration could be written as v squared over r, but it can also be written omega squared r. And if you're on a turntable, every point on the turntable has the same omega, the same angular velocity. If you draw a bunch of dots on the turntable so that they form a line out there, if you wait half a revolution, those dots are all going to be still lined up, pointing away from the center of the turntable. Okay, they've all turned through the same angle in the same amount of time. So the question says, will the Ladybug be more likely to slide close to the center of the turntable or out near the edge? Okay, that needed acceleration increases with the radius. So the farther you are out, the greater your acceleration is going to be, and the more friction you would need. But if you've maxed out the friction, you can't do any better. So you're most likely to slide far out near the edge. And actually, if R is 0, if you're right at the center of the turntable, you don't need any friction at all to stay there. So you could have a sheet of dry ice there and you wouldn't slide. If the Ladybug is 15.2 centimeters from the center of the turntable, at what angular velocity will the Ladybug begin to slide off the turntable? Well, I think we can do that. This is the maximum acceleration that friction can provide. We can figure out what omega max is for the radius that they gave us. And so let's start with that. Mu sub s g equals omega squared r. They gave us a value of r, so we'll divide that out. Mu sub s was 0.87, so we'll plug in the numbers here in a second. Actually, let's take the square root of both sides first. So omega, the maximum angular velocity, will equal mu sub s g over r. By the way, something else I do is on every equation, every problem I solve, I write stuff in variable form first. That's what this is, and this, and all of these things. I haven't plugged any numbers in yet. If you solve your problems that way on the test, I can at least see that you know the right formula. And then if you make a mistake punching it into your calculator, you've done enough work to get 4 out of 5 on the test. So keep that in mind. Okay, and mu sub s is 0.87 times g, 9.81 meters per second squared. Unfortunately, they gave me that in centimeters, but 15.2 centimeters times 1 meter over 100 centimeters. Divide this by 100 and you get 0.152 meters. So that's the unit conversion for that thing. If you're a little sketchy on converting from centimeters to meters, write it out this way and you'll save yourself. What you have to remember is that 1 meter is equal to 100 centimeters. So, and if you practiced enough with a meter stick, pick up the meter stick, look at the units on it, they're generally centimeters, and there's 100 of them in a meter. So that's worth knowing. All right, anyway, 0.152 meters, and we'll finally get omega here. And I forgot to hit the square root first. So I'll take the square root now, which I can do using my caret key. Actually, this one doesn't have a caret key, but if you get a number and you want to take its square root, you can use the caret key and then just enter 0.5, raising it to the 0.5, which is equal to 1/2, is the same as taking a square root. So, and I get 0.76, and with that we've only got two sig figures, so 0.76 radians per second, which is not very fast, actually. If we wanted to convert that to revolutions per minute, and if I multiply that by 1 revolution over 2 pi radians, and multiply that by 60 seconds over 1 minute, I could figure out how many revolutions per minute we're going to get here. Let's see, times 60 divided by 2 pi, I think. And I'm wrapping the denominator in parentheses. And I only get about 7.3 revolutions per minute, which isn't very fast. So this wasn't an old record turntable that turned at 33 1/3 revolutions per minute. The bug wouldn't be able to stay on that. So, okay. Do you have any questions on that one? We'll do some more of these rotational type of Newton's law problems on Monday, and maybe just a couple more. I'll record some of the ones that I did yesterday, except I'll clean them up a bit so I'm not getting it to a certain point and not being able to go further. But we'll do that. And then we'll also have some review on Monday. So I'll try to post last year's test and a review sheet. And on this review, I'm going to stress that last year's test is not the one you're going to be taking, that it'll be a different test. It's just there for practice. So have that stuff. Let's see, did anyone get a chance to look at the Atwood's machine lab yet? I'm wondering if that stuff is clear enough to work from. Try to have a look at it in the next day or two and send me an email if you need more information on it so I can fill the gaps if there are any. Okay, otherwise, have a good weekend. And this recording I should be able to post without problem. It looked like it continued recording the whole way. So anyway, see you on Monday.